Okay, hello everybody. I hope you are doing well. Do you hear me well? Okay, fine. Okay, let's start. We are in week 9. And today's subject is clustering, as you already know. So I open this one in Colab, as always. Okay, clustering. This is the first thing to mention is that it is unsupervised learning. It means that we have unlabeled data. In contrast to classification or regression, which was supervised learning, we had labeled data, so we had X and Y. And in this case, we have only X. Yes, and the objective of clustering, of course, are to organize the data into classes. And the objective is to have a high degree of intra-classes similarity and a low degree of inter-class similarity. And similarity is always a sort of distance measure. So we want a low, short measure, distance measure between elements of the same class or of the same cluster, and a high, great distance measure between elements of different classes, different clusters. The second objective of clustering is to find, this can be to find the class labels. We will see this in section 3, for instance. And then we can also think to find a natural grouping between objects, for example. You saw during the class that there are 2 types of clustering. And clustering, of course, is written with L. Partitioning algorithm like k-means and hierarchical clustering. So like we will see agglomerative clustering. This can be top-down. For instance, we will see this. And the aim of this laboratory session is to implement, of course, but also to compare them, as you also saw during the class. The time complexity of both algorithm is different, and we will see this in the second part of this lab session. Okay. As always, I will start with basic examples, so k-means and hierarchical clustering. Then, as I already said, the runtime complexity comparison. Then we will go through a real example of customer segmentation. And finally, we will compare clustering and classification, k-means and logistic regression. Okay. Of course, if there is any question, feel free to ask. And let's start. Okay. For those who don't use the dark background, you may have to change the style that I use. So you can write, if I run this, plt.style.available to see all the style you can use, because you won't be able to see the example if you don't have the dark background. So change this and use one of this one to make sure you see the y-axis, for instance. If I short run this, if you are not in this mode, you won't be able to see the axis. Okay, so either change this or change in the settings of Colab the dark background. Okay, first of all, k-means in one dimension. So we will work with a set of grades, of students' grades, which range between 0 and 100. There are 36 grades. And if we plot them using a scatter plot, we can see that there are basically 4 clusters. So the worst student, normal student, good student, and excellent students, for example. And if you want to fit a k-mean algorithm, we want to fit it with different k, so the number of cluster, and this, if I want to fit it with 2, 3, 4, and 5 clusters. So I create an instance of the class with k cluster. So this k-means class you can find in sklearn. I can show you. So this one. So we use this one and we use a number of cluster of k, which changes. And here are the other parameters. You can read this on your own if you want. So we change the k between 2 and 5. We fit the model on the grades. We get the centers because we want to plot them. We predict using the predict methods for the same for grades, and then we plot the grades with the color changing according to the prediction. We plot the centers in yellow, and we also set a nice title to it with the number of cluster. And this is to make a bit of space between the plots in the subplots from pyplots. Okay, if I run this, we can see that with 2 clusters it works already good. With 3, okay, it's fine. We have 1, 2, 3. But the best is with 4, as we already saw, where we have those 4 clusters. And if we try with 5, we can see that it starts to be a bit like close to each other, and we don't want this. Okay, the methods, the method to find out the optimal number of cluster is called the elbow methods. I think you saw this in class. So the idea is to plot the objective function, and in this case, the objective function is the square distance of each instance to its center. So this square plus this square plus this square, and so on and so forth. And we plot this, and as soon as we see a sort of elbow, we will see this. Then it means that it doesn't reduce the cost function anymore a lot. So you have the optimal number of cluster. In this case, we can see that if we increase the number of cluster from 2 to 3, we reduce a lot the sum of square error. Then if we increase from 3 to 4, we also increase a lot we also reduce a lot the sum of squared error. This is not actually error, but of square distances. And if we go from 4 to 5, then we don't reduce it anymore a lot anymore. So the optimal number is 4 in this case. And in this case, we can see this very clearly. And we will see later that sometimes it is not so obvious to see the optimal number of cluster from these plots, but in this case it is. So that's it for the so-called elbow methods and the basic example on k-mean. Any question on that, on this? Can we define, Pierre asks, can we define that mathematically? I guess the number of cluster. Okay, how do we do if it's difficult to distinguish the elbow? I don't know if we can define it mathematically. Maybe you can take a certain difference or percentage difference, and when it's below a certain threshold, then you can say, okay, that's my number. I don't really know, but the point is that if there are a number of cluster, a defined number of cluster, if clustering is the appropriate algorithm for this problem, for this data, then there will be an elbow at some point if you plot this. Because if you have like random points, think of you only have this, then you won't have any elbow. So if it's possible, or if it makes sense in the data to have cluster, then you will automatically have an elbow at some point. And the more it's possible to cluster, the more will be, you will see this clearly, I think. So again, if you have points without clusters, if it's not clear, imagine you only have this, then you won't see any elbow. And if you have clusters, then you will see. And you will be able to determine, to find out the optimal number. I think there was. Inertia from Brian. Inertia means that the more cluster you make, the less distance between sample you have. Yes, because inertia is, if we go to the class, it's always good to go and read the documentation. So the inertia is defined as the sum of squared distance of samples to their closest cluster center. So this is basically the cost function that you try to optimize, to minimize when running the algorithm. So basically, if you look at this is the distance of the sum of the square distance of each of those points to this center, and each of those points to this center. So this minus this squared plus this minus this squared, and so on and so forth. So, and it's obvious to see that when you have the optimal number of clusters, this distance is each time reduced a lot, and then not so reduced, because the difference here is not so big, as you can see. How do you choose here from 4 or 5 clusters? Because 5 also seems good on the graph. Yes, you can also, it depends what is the problem you want to solve. But in this case, The optimal number is 4 because it reduces a lot from 2 to 3, from 3 to 4, and from 4 to 5. It doesn't reduce a lot the inertia because those centers are very close to each other. But if you want to take 5 and your problem and your solution is better with 5, then you can take 5. This elbow method is only a good way to see what happens. But in this case, 4 is the optimal, and you will see that each time the elbow is the optimal. Okay, so that was it for k-means. Then hierarchical clustering. In order to show this, I have 9 points from 0 to 8. If we plot them, we can see that there are 2 or 3 clusters. So either you take 1 and 2, or you take 1, 2, 3. There is one question. Is it possible to show again what we need to add in the code if we don't have dark mode? Yes, of course. You can take one of those slides, for instance, classic, fast, something that is not dark, so not dark, not this one, and change this here. And you will see that the plots look different. So at the beginning. Okay, we had 9 points, 0 to 8. If we plot them, we can discuss this, maybe 2 or 3 clusters, either 1, 2, or 1, 2, 3. In this case, we need to have distances. So we use this pairwise distance from the data, and we compute the Euclidean distance. And we show this in a heat map from Seaborn to make it beautiful. And we can see, for instance, if we take P0, the closest point to P0 is P6, which is the case here. Then it's P4, then P8, P4, P8, then those 3, which are around like 0.4, 0.40 distance, the Euclidean distance, and then the farthest points with 1 and 1. There's one question. I also didn't get the dark mode thing. Okay, let me re-explain. If I change this, in this case, I use the dark background style, and it makes like plots this like this. And if I change this, I can change this to show you and use one of those. So maybe classic. Then it will plot the stuff. If I go to a plot, it will plot the stuff differently. And if you have not the dark mode of collab, you can change this in the parameters, like in UT. You can change it like here. If you have the light mode, then you will be able to see this. And if you have, and if I change this and use the dark background, then the plots Okay, it works. It works. But we are not able to see the title. Like here, we don't see the title and the K, and we don't see the access. That is what I meant. But maybe if I do this again, it works. Yes, yes. In this case, it works. Okay, I didn't know this. Okay. Okay, fine. So you can use basically what you want. Sorry for that. Let me change this again. Okay. So this to say that you can change the style, and I thought it was you wouldn't be able to see those numbers on the axis, but basically you can see this in light mode, so it's okay. Okay, well, yes, here. The distances. So that was it for the distances basically, and then we can use we can plot the so-called dendrogram, the tree. First of all, with the single linkage. So we use this SSTH.dendrogram, and then we have the linkage single, and then we plot this. So basically this plotted. And if we run this, we can see that P0 is first attached to P6. So if we go back to the plot, it's first attached to P6 because it's the closest point. Then both of them are attached to P4, and then the 3 to P8, which makes sense here. P4, both of them to P4, then the 3 to P8. Then all 4 to those ones, to P3, P5, and P2, which is the case here. P3, P5, and P2, all 4. And then 1 and 7 to all of them. And we can see here that we can choose basically the number of clusters. If we want to take 2, then we have 1 here and 2 here. And if we want to take, so we cut here. And if we want to take 3, then we want to cut here, and we have 3. 1, 2, 3. And it's interesting to see that it's a bit different with complete linkage, as you can see here. P0 is attached to P6. It's also the case here, but then both of them are attached to P4 and P8. And this is because with single linkage, it takes the minimum distance. So for instance, between P4 is here attached to P0 and P6 first, because the minimum distance is P0 is here, P4 is here. The minimum distance is 0.06, which is below P8, so it's first attached to both of them. And with complete linkage, it takes the maximum distance, so P4 is first attached to P8 because it's smaller than the greatest between this one and this one. So that's the difference basically between single and complete linkage. So you can see this here. P4 is attached to those ones first, and then to P8. And in this case, first to P8, because the P8 is closer to P4 than the maximum of those ones. What do you mean by minimum distance? Question in the chat. The minimum distance is, for instance, I can re-explain this. The minimum distance from one point to a cluster is the minimum distance of this point to all the points in the cluster. So for instance, the minimum distance of P4 to the first cluster, this one, 0 and 6, is the minimum of P4 to 0 or P4 to P6. And in this case, the minimum of P4 to P0 and P4 to P6 is this one, which is below this one. That's why with single linkage, you have first, P4 is first attached to P0 and P6, and then to P8, and with complete linkage, P4 is first attached to P8 because this is smaller than this one. So with complete, it takes the maximum distance of the point to the cluster. Okay, I know I have to run this first. So we do the same as with k-means. We want to plot with different number of clusters. So with 2, 3, and 4 in this case, and we use the agglomerative clustering. So agglomerative clustering. This one, you can specify, of course, the number of cluster, and it does the, and you also have to specify the linkage, of course. In this case, the default is word. I guess you don't saw this in class, but it's sort of an average, and you can specify complete or single in this linkage here. So, and if we run this, so we use the single linkage in this case, and then we fit predict with the data and we plot it. So for k equals 2, 3, and 4. And we can see that we have what we already saw. With 2, it makes like one cluster here and one cluster here. With 3, 1, 2, 3. And with 4, it begins not to make sense anymore. Any question on hierarchical clustering? Okay, if it's not the case, we can then go through part 2, which is an exercise for you. The well-known participation exercise. And the aim of the exercise is to compare both algorithms, so k-means and hierarchical clustering, in terms of computation time needed to fit. So we saw in the class that k-means is linear and hierarchical clustering is like N2 or N3. And we want to show this basically. So I created for you a function that generates 3 clusters you can specify the number of points you wish. So the centers, the standard deviation of the cluster, and then you use the make blobs function with a number of sample equals to num points that you specify in the function. Then you specify the standard deviation and the centers. You want 3, and you can specify the random state to have always the same. And if I use it as example here. And this, so I use my function to generate x and y. I can also show what is x, how x look like. So basically it generates a sample of points that belongs to 3 clusters of, in this case, 100 points. Okay, so we have a function to generate 3 clusters, and then we want to generate 3 clusters for different number of points, sorry. So from 100 to 25,000. And then we want to store the returned x. So what I showed you. So those 2 coordinates points. in a list. So you have to generate 3 clusters and then append X to the X list, and then use what I showed you earlier, so k-means and agglomerative clustering, and you can time it as you wish. And I show also an example of how to time something. So with the time package. So you use the time, the method time from the time package. And this is an example. I do some calculation, a large amount of times, and then I have the difference, which is the completion time. So you put it where you want the start, then you end it, and then you make end minus start, and it gives you the time, the elapsed time of the stuff, in this case 0.58. And you can see that it changes a bit if you run this many times. And then you have to record the time. So for each X in X list, you have to create the model with 3 clusters, the k-means, then fit it and record. So you will have to start the time, then fit, then end the time, and then append the time to the k-means, and then do the same with this agglomerative clustering with 3 cluster again, and then append it again, and then plot it at the end. And we will do this in groups. Okay, there is. Okay. So any question on what is to be done for this exercise? This shouldn't be so difficult. Basically, everything is here, and you have to complete where it's written complete. And then you have to send me your code and a screenshot of your plot on Slack to get the points. And everybody has to do this like last time. Okay, so let's break out the session. Okay, do we have to send you the Jupyter notebook? If you wish, but I prefer to have only the code. So you copy from here, you copy and paste this, you copy and paste this, and you copy and paste this, the 3 parts. And how many time do we have? How many time do we want? I don't know. 20 minutes maybe. 2 days. Yeah, you have to send it to me before today's evening, before midnight. Yeah, maybe 20 minutes. And if you don't finish, like you can do this this evening and send it to me until midnight. Okay, let's break out the session. Okay, four people. Okay, so until 4 until 10 past 4. So that's basically the solution. And I will upload this notebook at the end, this version of the notebook at the end, so that you can have access to the solution. Okay, how was the exercise? Easy, difficult? Basically, the best way to send it to me is to send me only screenshots of your of what you did on your Jupyter notebook. That's the best way to send it to me. I can show you. To answer your question, Inessa, the result should look like this, basically. So I don't show you the code, but the result should look like this. So with hierarchical clustering, which takes a lot of time to complete, and K-means with basically linear and flat. But you can have other type of plots, that's also fine. Okay. So let's now go through a sort of real life example on customer segmentation. So we load as always the data. We have 200 customers with their ID, gender, age, annual income in 1,000, and spending score between 1 and 100. So this is mall data, customer mall data. You can find the data on Kaggle here. So yes, we have 200 customers. Without null values, without anything that has to be changed, integer object, everything's fine. Or we have to change this, basically. The gender, we want to change the gender. We don't want male and female. Actually, we want 0 and 1. So we use, as always, this as type and then cat codes. We already saw this in many lab sessions. And this yields something like this, where we have the gender 1 or 0. So all variables are now numerical. So we had to change basically this one. So there was something to change. If we describe the data, we can see some information, mean, age, annual income. The age range from 18 to 70, for instance. Okay. And the aim is basically to make cluster of customer. So we don't have any class, we don't have any column feature with 0 and 1 or with something to predict. We only have attributes, and we want to use them to cluster the customers. So as we already saw, there is no null value, and we can use this piece of code to plot to make beautiful plots of the variables to see a bit, well, how do they look like. So we see that there are basically a bit more than 100 0 gender. I guess this is, I don't know, maybe it's woman or male or female. Let's see, male is 1, female is 0. Okay. So there are a bit more of women in the sample. Annual income looks like this. So a lot of average people and not so many rich people. Spending score, age. We can also do a bivariate analysis. So using this pair plot from Seaborn and this. And basically the EDA is very important in this case. Is always important to do a bit of exploratory data analysis. But in the case of clustering, it is really, really important because you can then see, for instance, here, you can see that we can do something with clustering in this case. There are 5 clusters, we can see them in this case. So we're using those 2 variables, those 2, so annual income and spending score, for instance. So EDA is always important, but in clustering, it's more than important because we can see if there are relationship, if this is possible to do clustering with the data, basically. Okay. First of all, then the k-means algorithm, and we want to first determine the number, the optimal number of cluster. We already saw this. In this case, with those 2 variables, we see that we may think we have 5 clusters, but with 3 variables, we don't know because we cannot do. Yes, we can do a 3 variate plots, but it's a bit difficult. And then with 4 variables, we don't know. So it's always also very useful to plot this, to do this elbow method. So this, what we saw at the beginning. So this is a function to plot the inertia of a variable. So you take the variables of the data frame, and then you plot you compute, you fit the model, the k-means with k from 2 to 20, and then you append the inertia and plot it. So this is a function, and we will use it with different variables. So first of all, with the 2 we saw, so this annual income and spending score. So those 2, and this should result in a number of cluster of 5. Let's see. So I use the function I defined here with those 2 variables, and we see in this case this is not so clear like at the beginning, but we can see that the elbow is in this case here. So we have a big decrease of the objective function, and then it decreases less. And so the optimal number of cluster in this case is 5, which was expected because this confirms what we saw in the EDA here or here. So this is basically the same but reversed. And if we want to try with 3 variables, so we add the age. We know how annual income, spending score, and age. This yields something like this. And in this case, this is again less clear, but maybe 6 is fine. So we see a bit of elbow in here. So it decreases, and then a bit less. So we may think of using 6 cluster in this case. But again, this means that this will not be perfect because we don't have this clear elbow. So the clustering algorithm will work, but not so. So the center will not be at the center of the of different clusters that are really separated to each other. In this case, this is a bit better. And with all 4 variables, so I add the gender. This is again not so clear, but we may think of using again 6 clusters in this case. Okay. In the case of 2 variables, annual income and spending score, we can plot the cluster for a number of cluster of 2 to 6. So we use those 2 variables. We create an instance of the class with k cluster 2 to 6. Then we fit on the new df. Then we get the center. We predict to have the colors here. And then we plot this, plot the centers and set the titles and labels of the axis. And if I run this, we see that with k equal 2, it's not so good because we don't set, we have a low, we have here, we don't know what to do with this. They are really very close to each other and does not belong to the same cluster. In this case, this is better. This should work. This could work. 3. 4 is again better, but the best is 5. And with 6, it starts to not make sense anymore. So optimal number of cluster is 5. And then this is one of the objective of clustering. We can then label the classes. So we can label the clusters to have classes. And in this case, we may think of, if I take the 5, having this class customers who earn little, so annual income is low, spend little, these are the reasonable poor. Then we have the senseless poor because they spend a lot and have little earnings, income. Then we have the average people, average. Then we can think of the rich, high annual income and high spending. This is basically this should be the target of our marketing efforts. If you would use this data for marketing purposes, for instance, and then the stingy, which earns a lot but do not spend a lot. So this is an example of how useful is clustering. Then you make the clusters and then you can label them and then you have classes. Okay, any question on that? Yes, there is one. How do you use the result to label the classes? Yes, that's what I did here. That's an example from me. So I first do the clustering with those 2 variables, and this gives me this. And then I can think, okay, what does this cluster represent? If I have to label it, basically these are people which have a low annual income and do not spend a lot. So I can say, okay, these are the reasonable poor. So poor people that doesn't spend a lot, reasonable poor. Then we have this cluster, people who earn not a lot but spend a lot, and I can say, okay, these are the insane poor or senseless poor, if you wish. Then average people, because they earn average and spend average. Then the rich, and then the stingy. But this is for me, so basically you do the clustering and then you can think, okay, what does this cluster represent? And this one, and this one, and this one. So you save the result from model predict, and those are the labels. I don't understand this question. The labels I found out myself, because with clustering there is no label. This is unsupervised learning, so you don't have label. We only use k-means, so this belongs to this cluster because this center is the closest one to this point, and this belongs to this cluster because this center is the closest one to this one. So we don't use label. We first cluster the customers, and then we can think, okay, what does this may represent, or how can I label this if I would like to label this? This is one of the objectives of clustering. But basically, you don't. If you see the function, this is only to predict. If I just print the pred, the last pred, just give me the cluster. This gives me the cluster of each point. And I use it just to color the cluster. So this is not a class, this is a cluster. Because I don't fit on X train and Y train on a training on X and Y, I only fit on X basically, because I only have features. I don't have any class to predict. And then once this is done, I can think, okay, what can this be? Does it make sense? Is it clear what I explained? Okay. So, and there is an example here with 3 variables. You can look at it on your own. I can show you if it works. It's at the end. So this is with 6 clusters, 1, 2, 3, 4, 5, 6, and 3 variables. So the 2, if we do this like this, we can see the 2 annual income and spending score, x-axis, and then the age. And we can see, as we also defined this, that we have 6 clusters with those 3 variables. So this gives something like this, but it didn't work in Colab to have some interactive plot. That's why I show you like this. So 1, 2, 3, 4, 5, 6 clusters. Okay. And now we can do the same basically with hierarchical clustering. So we create an instance of this class and use a k from 2 to 6. Then we use the complete linkage and the Euclidean distance. And we use this fit predict to get the assignment. So basically I can also show you what assignment, but assignment is like the prediction. So this is the cluster to which each point belong. And then I use it to color the plots. And as before, I do a scatter plot of this with a beautiful title and labels, and this yields something like this and we can see that with 5 is also great and even better than in the k-mean case. Because it can k-means one of the disadvantages of k-means is that it is only for cyclic or cycle clusters, and in this case they are not so So with hierarchical, we have a better result. And again, 5 is the best, but you can use 3 if you want to separate rich and poor people, maybe. So rich and poor people, or 2 even. And with this hierarchical clustering, we can also plot the tree, so the dendrogram. This is called the dendrogram. I use here complete, and then you choose where you want to cut it to have the. So you saw it takes more time to run, like in the exercise, and then you can see, okay, you can say, okay, I want 2 clusters. Then I cut here and I take those ones, this one and this one. If I want 3, I can take the green one, the red one, and the blue one. And if I want 5, we have this one, this one, this one, and this one, and this one. 1, 2, 3, 4, 5, maybe. So it depends on where you want to cut. And if we use single linkage, this is interesting. Basically, it doesn't work. So it may not work depending on the linkage you use. And I can show you this, what it gives if I change this to single. And this yields something that does not make a lot of sense. So there is only 1 point because they're all grouped in the same one, because if you use single, you take the minimum distance, and then the minimum distance of this point to this cluster will be always this point, and then this point, because this point is too far from the other one, and this is the same from with all those cases, except here probably you have those 2 points not together. But so be careful which linkage you use. It can yield very different results. And there is also word. Let's see if it works. Yes, it works with word. Okay. And as we already see complete, you take the maximum, that works as well. Any question on this hierarchical clustering for customer classification? Okay, if there is no question, we can go through the last part. We compare clustering and classification, k-means and for k-means and logistic regression. So we need labeled data. So I use a data set of emails, which looks like this. So this is basically you classify the email as spam or not spam. One is spam, 0 is not spam. And then you have the text is already you already have this vectorizer. So I don't know what it does, but you have numbers that represent the words. So, for instance, the word frequency of the word will is like 0.64. Maybe it's normalized because 0.64, it's big. So you have word frequency of, sorry, of a lot of some words, and then you have the class, and also you have this. So basically 58, I guess, I think, if I remember well. Yes, so 57 features and one target. And we have 4,601 mails. In this case, the base rates, we have two classes. So the base rate is the probability of the most common class. So this one, which is not spam, and this one is spam, which is around 60%. And we have to bid this, and we will do this. We will bid this. So I use again this k-fold cross-validation and the accuracy score metrics and the logistic regression. So I compare the k-means and the logistic regression. I first select the variables, so our x is everything except class, and our y is this class, so this spam or not spam. And I define the k-means with two clusters, of course, because we have two classes. And I define the logistic regression. I gather them into a list, and then I use this cross-validation with 10 splits, sorry. So basically, it split the sample into 10 subsample that are random, and it trains the model on nine samples, and then test for the last one and do this 10 times while changing the test set. And then sorry, I want the mean across the samples, the mean of the prediction accuracy. So this accuracy, which is defined as the number of correct prediction divided by the number of in the test sets. And I do this for both algorithm, and then I print the accuracy. Okay. And of course, with k-means, I already said this, but this is important. You have two clusters because you have two class, but you don't use the y to fit the model. You only do you only fit the model on x. So on those ones, and then you predict for the rest, for the rest of the points of the test set, to which cluster they belong, and compare this with the y test. And if I run this, we can see that for k-means, for the first one, this yields like an accuracy score of 64%, which is just above the base rates. And for the logistic regression, there is no, we would say in French, there is no photo, with 92%. And if I run this again, I guess it can change. This one can change, but this one doesn't change. So it is around base rate with k-means and 92% with logistic regression. So the conclusion is written here of this part. So you have to use classification algorithm for classification problems. So if you have labeled data, use classification algorithm. This will always give you better results, a better precision. But if there is no label, or if you want to label data, to label unlabeled data, then you can use clustering. Okay, any question on this and on this wall, or on this wall lab sessions? Okay, if this is not the case, oh, there is one. From Luca. One question for today exercises. How are we supposed to define our plots for the time axis? For the time axis, you can use the num point for the x-axis. You use the number of points, so 100. There is one list with 100 to 25,000, and for the y-axis, you can use the time. So you plot the number of points in the sample, and the y-axis is the time elapsed, the completion time of the algorithm. Okay, so the lab session is over. I stay like 5 to 10 minutes to see if there are other questions. You can ask also question on other topics if you want. But the lab session is now over. I wish you a nice evening, and we will see each other next week. Thank you for attending the lab session, and see you soon. Question from David. I am getting a different accuracy score than you. Yes, this is normal because the k-means algorithm is initiated with random centers, and this can then yields different result, different clusters. So this can change because the centers changes, and then when you want to predict, then one point may be like closer to one other center than the one previously. And this shows also that basically k-means is not useful for classification. It's only useful for clustering. Question from Brian, what kind of plot did you use for the exercise? You can use what you want, whatever you want, whatever makes sense. I use a scatter plots. plt.scatter. You can use a bar plot. You have to show that with hierarchical clustering, it takes much more time than with k-means.